The nearest star to our Sun is a dim red dwarf called Proxima Centauri. It sits about 4.24 light-years away, a distance so vast that even describing it in miles starts to feel meaningless. In miles is roughly 25 trillion of them. In kilometers, closer to 40 trillion. If you boarded the fastest spacecraft ever launched by humanity and aimed it straight at Proxima Centauri, the journey would take somewhere between 17,000 and 75,000 years, depending on which probe you chose. For context, 17,000 years ago, humans were still living in the Ice Age. Woolly mammoths were still walking the Earth. Agriculture hadn't been invented yet. And that's the closest star. There are roughly 400 billion stars in our galaxy alone, most of them far more distant. The scale of the problem isn't just engineering, it's almost philosophical. Getting to another star isn't like building a faster car or a bigger rocket. It requires rethinking what a spacecraft is, what a journey means, and in some cases, what physics itself allows. But here's the thing, the options aren't zero. Scientists, engineers, and physicists have spent decades, some of them entire careers, mapping out every conceivable path from here to there. Some of those paths are within reach of current technology or close to it. Some would require advances we haven't made yet but can imagine making. And some live at the outer edge of what the laws of physics might theoretically allow, where the math works on paper even if the engineering seems almost impossible to imagine. Every single one of those paths deserves a serious look. Because the question isn't just academic. Stars host planets. Some of those planets sit in the right zones for liquid water. Some of them might already carry life. The only way to find out for certain, not just from a distant telescope, but up close, with instruments in orbit or rovers on the ground, is to actually go. And so the question of how becomes one of the most important questions our species has ever asked. Before getting into the methods themselves, it helps to understand exactly why this is so hard. And to be honest, most popular accounts understate it. Speed is the obvious issue, but it's not the only one. The real problem is energy. Specifically, how much energy it takes to move any meaningful mass fast enough to reach another star in a useful amount of time. A reasonable target for a crewed mission might be arriving within a century, ideally within a single human lifetime of 70 to 80 years. To do that, a spacecraft would need to travel at somewhere between 5 and 20% of the speed of light, depending on the destination. The speed of light is about 186,000 miles per second, or roughly 670 million miles per hour. 5% of that is still 33 million miles per hour. 20% is 134 million miles per hour. Now consider that the fastest human-made object ever built, the Parker Solar Probe, which uses the sun's gravity to slingshot itself to extraordinary speeds, tops out at just under 400,000 miles per hour under the most favorable conditions. That's already staggeringly fast by any everyday standard. It would take you from New York to Los Angeles in about half a second, and it is still roughly 80 to 300 times too slow to make an interstellar trip within a human lifetime. The gap between where we are and where we need to be isn't a small engineering problem. It's orders of magnitude. To put numbers to it, achieving even 10% of the speed of light requires roughly 100 million times more energy per kilogram of spacecraft than a typical chemical rocket delivers. A ship the size of a school bus, accelerated to that speed using only chemical propulsion, would need more fuel than exists in the observable universe. That's not hyperbole. That's the math of what's called the rocket equation. The more fuel you carry, the heavier the spacecraft. The heavier the spacecraft, the more fuel you need to accelerate it. And that relationship grows exponentially, not linearly. Chemical rockets hit a wall very quickly in that equation, and interstellar distances are so far beyond that wall that chemical propulsion is essentially ruled out before the conversation even starts. So every serious proposal for reaching another star begins with a fundamental departure from the kind of propulsion we use today. Some of those departures are incremental extensions of existing technology. Some are radical reimaginings. And a few are based on physics so strange that they feel more like philosophy than engineering. Except that the equations behind them are real. The simplest extension of existing technology into the interstellar direction is electric propulsion. And the most developed version of that is the ion thruster. Ion thrusters work by ionizing a propellant, usually xenon gas, using electricity, and then using powerful electric fields to accelerate those charged ions out the back of the engine at very high speeds. The thrust produced is tiny. A typical ion thruster puts out about as much force as the weight of a single sheet of paper resting on your hand. In the near vacuum of space, with no friction and no gravity to fight, that tiny continuous push adds up over time to produce speeds that chemical rockets can't match for long-distance missions. NASA's Dawn spacecraft, which visited the asteroid Vesta and the dwarf planet Ceres, used ion propulsion. So did the Japanese Hayabusa missions to asteroid samples. The European Smart 1 lunar orbiter used it. These aren't experimental curiosities. They're proven operational technology flying in space right now. The appeal for deep space is efficiency. The measure engineers use is called specific impulse, which is essentially a measure of how much thrust you get per unit of propellant. Chemical rockets have specific impulses around 450 seconds. Ion thrusters reach 3,000 seconds or more. That means for the same amount of propellant mass, an ion thruster can achieve far more velocity change. The problem is time. Ion thrusters accelerate slowly, very slowly. Getting a substantial spacecraft to even a fraction of a percent of the speed of light on ion drive alone would take decades of continuous thrust, and you'd still fall absurdly short of what's needed for interstellar travel. The technology's sweet spot is within the solar system, for missions to the outer planets or beyond. At interstellar scales, it simply can't bridge the gap, not without a dramatic improvement in either the power source driving the engine or the exhaust velocity the engine achieves. That said, more advanced versions of electric propulsion, using plasma instead of ions, or magnetic fields to contain and accelerate superheated gas, push those limits further. VASIMR, the variable specific impulse. Magnetoplasma rocket is a concept developed partly by former astronaut Franklin Chang Diaz that uses radio waves to heat plasma to temperatures hotter than the sun's core, then channels it magnetically. It can theoretically achieve specific impulses over 30,000 seconds. That's still not interstellar, but it represents a meaningful step up the ladder. The honest assessment of ion and plasma propulsion is that these technologies belong to the early chapters of the story, not the final destination. They likely power the probes and missions that operate within our solar system over the coming century, and they represent important building blocks. But reaching another star requires something fundamentally more energetic. One of the most elegant ideas in all of propulsion physics is the solar sail. It requires no fuel at all. It works on a principle that most people don't immediately think of when imagining a spacecraft engine. Light has momentum. Photons, or particles of light, carry no mass, but they do carry momentum, as described by quantum mechanics and special relativity. When photons hit a reflective surface, they push it ever so slightly. A single photon striking a mirror imparts a force smaller than any scale you've ever encountered. But if you make that mirror enormous, kilometers across, and point it to the sun, the accumulated push of trillions upon trillions of photons becomes real, measurable thrust. And unlike a rocket, a solar sail doesn't run out of fuel. As long as light is hitting it, it's being pushed. JAXA, the Japanese space agency, launched a spacecraft called Icaros in 2010 that successfully demonstrated solar sailing in deep space, becoming the first spacecraft to use sunlight pressure for interplanetary travel. LightSail 2, operated by the Planetary Society, successfully raised its orbit using solar sailing in 2019. These are real results, not simulations. The limitation for solar sails is that sunlight spreads out and weakens with distance. The further from the sun you get, the weaker the push. By the time you're out past Jupiter, solar pressure is almost negligible. A sail pushed by sunlight alone can accelerate nicely through the inner solar system, but it can't maintain that acceleration through interstellar space. One proposed trick is to fly the sail extremely close to the sun, closer than any previous spacecraft, in what's called a close solar pass or sundiver maneuver. The idea is to fold up the sail as you fall toward the sun, unfurl it at the closest point to catch a massive burst of solar radiation pressure, and then let that slingshot you outward at far higher speeds than you could achieve from a normal starting point. Computer models suggest this could theoretically propel a sail to speeds around 0.1 to 0.5% of the speed of light. Still too slow for practical interstellar travel within a human lifetime, but potentially fast enough for very long-duration robotic missions. The more powerful version of the solar sail concept replaces sunlight with a laser beam. A ground-based or space-based laser, pointed precisely at a thin, lightweight sail, can deliver far more intensity over far greater distances than the sun's natural light ever could. This is the operating principle behind Breakthrough Starshot, and it represents the most credible near-term path to sending something, even something tiny, to another star within a human lifetime. In 2016, a group that included physicist Stephen Hawking, investor Yuri Milner, and a scientific advisory board that has since grown to include dozens of leading researchers, announced an initiative called Breakthrough Starshot. The goal is to send a fleet of gram-scale spacecraft to the Alpha Centauri system within the next 20 to 30 years, using laser-driven light sails. The concept is deceptively simple. Build a sail made of an ultra-thin, ultra-light material, perhaps just a few hundred atoms thick in some places. and attach a tiny electronics package to it, no heavier than a paperclip or a small postage stamp. Then build a massive array of ground-based lasers and focus their combined beam on the sail as it launches into space. The beam pushes the sail to extraordinary speeds very quickly, over the course of a few minutes of acceleration. The target speed is 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take about 20 years. Given that the project was announced in 2016, if everything went perfectly, a probe could be sent within a decade or two and arrive in the Alpha Centauri system sometime in the second half of this century. There's nothing physically impossible about this plan. Every component, including lasers, thin film materials, and miniaturized electronics, is something that already exists in some form. The challenge is scale. To push even a gram-scale spacecraft to 20% of light speed, the laser array needs to deliver roughly 100 gigawatts of power for a few minutes. That's comparable to the combined output of dozens of large power plants, all focused on a target the size of a postage stamp, moving at increasing speed through the atmosphere and into space. Maintaining beam focus over those kinds of distances and power levels is an enormous engineering challenge. Atmospheric distortion, thermal effects on the laser optics, keeping the sail stable under the force of the beam, these are all solvable problems in principle, but solving them in practice will require advances that haven't been made yet. The sail material is another frontier. It needs to reflect almost all the laser energy hitting it, because any absorption turns into heat, and at those power levels, even a fraction of a percent of absorption is enough to destroy the sail. It also needs to be rigid enough to hold its shape under the beam pressure. And it needs to be light enough that the power-to-mass ratio is sufficient for the target acceleration. Groups around the world are experimenting with materials like graphene and engineered metamaterials that could potentially meet these requirements. But nothing ready for flight exists yet. Then there's the question of what such a probe could actually do at the destination. At 20% of light speed, the spacecraft flies through the Alpha Centauri system in hours. It has no way to slow down, there's no laser array on the other end to decelerate it, and it carries no fuel. All it can do is take measurements and images as it screams through and transmit them back to Earth. The signal would take about 4 years to arrive home. What you'd get is a brief snapshot. But a snapshot from another star system, taken by humanity's first interstellar probe. That alone would be extraordinary. For all its challenges, Breakthrough Starshot represents something genuinely new. A proposal where the physics is unambiguous, the technology is recognizable if not yet sufficient, and the timeline is measured in decades rather than centuries. It is, by most assessments, the most credible candidate for humanity's first interstellar mission. While laser sails represent the cutting edge of near-term thinking, there's an older branch of interstellar propulsion that goes back to the earliest days of the space age, and it's built on a far more straightforward idea. Use nuclear energy, which is millions of times more energy dense than chemical fuel, to power the engines. Nuclear fission, splitting heavy atoms like uranium or plutonium, releases energy on a completely different scale than burning chemical propellants. This was understood by physicists from the moment the first atomic bombs were tested. And it wasn't long before people started asking whether that energy could be used for spacecraft. The most direct application is nuclear thermal propulsion. Instead of chemical reactions, a nuclear reactor heats a propellant, usually liquid hydrogen, to extreme temperatures, and the heated gas expands and is expelled through a nozzle to generate thrust, just like a chemical rocket, but much hotter and therefore much faster. NASA actually tested nuclear thermal rocket engines in the 1960s under a program called NERVA, or Nuclear Engine for Rocket Vehicle Application. The engines worked. They demonstrated specific impulses roughly twice that of the best chemical rockets. Twice is significant for missions within the solar system. It makes trips to Mars faster and more fuel efficient. But for interstellar travel, double isn't nearly enough. Nuclear thermal propulsion gets you to speeds of perhaps 30 to 50 kilometers per second. To have any realistic shot at reaching another star within multiple human generations, you need speeds in the hundreds or thousands of kilometers per second. The gap is still enormous. The more ambitious nuclear option is a fission fragment rocket. Instead of using a reactor to heat a propellant, a fission fragment rocket attempts to capture and direct the actual particles produced when uranium or plutonium atoms split. Highly energetic fragments that emerge at incredible velocities, sometimes several percent of the speed of light. If those fragments could be aimed and used as exhaust directly, the specific impulse would be orders of magnitude higher than any thermal system. Theoretical designs suggest exhaust velocities that could achieve a few percent of light speed, potentially reaching Proxima Centauri in a few hundred years rather than tens of thousands. The engineering obstacles are severe. Containing, guiding, and surviving the radiation environment of the raw fission process is a formidable challenge. But the physics is real. There's a chapter in nuclear propulsion history that tends to make people do a double take. A serious government-funded study in the 1950s and 60s that proposed propelling a spacecraft by detonating nuclear bombs behind it. Not inside an engine, behind the ship. One bomb at a time, in rapid succession. Project Orion was no fringe idea. It was developed at General Atomics in San Diego, with physicist Freeman Dyson as one of its key contributors. Wernher von Braun, the man who built the rockets that took humans to the moon, issued a white paper supporting it. The United States Air Force and DARPA both funded aspects of the research. A physical test vehicle called Hot Rod was built and actually flown in 1959 at Point Loma, California, using conventional chemical explosives to test the pulse propulsion concept. It worked. The design called for a massive pusher plate at the back of the spacecraft. A thick, heavily engineered disc of metal. Nuclear devices would be released from the rear of the ship, one at a time, and detonated at a set distance behind the plate. The explosion's plasma and radiation would hit the plate, transferring its momentum to the ship. Shock absorbers between the plate and the inhabited sections of the spacecraft would smooth out the violent jolts. Then the next device would be released and detonated. And the next, at a rate of perhaps one explosion per second, or faster. It sounds insane. The engineering, according to Dyson and his colleagues, was completely workable. The large plate could absorb the blasts. The shock absorbers were mechanically straightforward, and the performance numbers were extraordinary. Designs for an Orion spacecraft capable of interstellar travel were calculated to reach speeds of 3 to 11% of the speed of light, depending on the size of the vehicle and the yield of the devices used. A large Orion ship, and designs range from hundreds to tens of thousands of tons, could potentially reach the nearest stars within a few centuries. The project was killed not by engineering failure, but by politics and public health. The 1963 Partial Nuclear Test Ban Treaty prohibited nuclear explosions in space, and in the atmosphere, and underwater. Orion, which would have launched from Earth's surface in its most aggressive early designs, scattering radioactive fallout across the globe, was incompatible with that treaty. Development stopped in 1965, and most of the detailed designs were classified. What makes Orion historically remarkable is that it was probably buildable. Not easily, not cheaply, not without enormous consequences for the environment. But the physics was solid, and the engineering was understood. It remains one of the few interstellar propulsion concepts that has ever been backed by actual hardware testing rather than just equations on paper. A more modern version, called Project Medusa, proposed in the 1990s, updated the concept by replacing the pusher plate with an enormous sail-like capture structure in front of the spacecraft rather than behind it. The explosion occurs ahead of the ship. The blast expands outward, the sail catches it, and the craft is pulled forward. This geometry turns out to be more efficient than a rear pusher plate, and it avoids some of the radiation exposure issues. Medusa remains a theoretical design, but one grounded in genuine physics. If nuclear fission represents the first generation of serious interstellar propulsion thinking, then fusion is the second, and it's the one that most physicists consider the real prize. Fusion is the process that powers the sun and every other star. It combines light atomic nuclei, typically hydrogen isotopes, into heavier ones, releasing enormous amounts of energy in the process. Per unit of fuel mass, fusion releases several times more energy than fission, and the fuel is among the most abundant material in the universe. The dream of a fusion rocket is straightforward. Achieve controlled fusion in a chamber. Direct the resulting plasma and energy out of a nozzle. And use the reaction products themselves as exhaust. No heating and external propellant. No bombs. Just continuous controlled fusion driving a jet of plasma at extraordinary velocities. In the 1970s, the British Interplanetary Society undertook a detailed engineering study of a fusion-powered interstellar probe called Project Daedalus. Over 5 years, a team of engineers worked out the specifics. A 2-stage fusion spacecraft, fueled by pellets of deuterium and helium-3, ignited by electron beams. The first stage would burn for 2 years, the second stage for another 1.8 years. Total mission, a flyby of Barnard's star, about 6 light-years away, in approximately 50 years. The calculated cruise speed was around 12% of the speed of light. Daedalus was not a fantasy. Every component was grounded in physics understood at the time, and the engineering conclusions were taken seriously. There were 2 main obstacles. First, helium-3, the preferred fusion fuel, is extraordinarily rare on Earth. The study proposed mining it from Jupiter's atmosphere. Second, fusion itself. In the 1970s, controlled fusion was already being worked on, and it was already proving difficult. Decades later, it's still proving difficult. though the situation has changed significantly in recent years. Project Icarus, launched in 2009 as a successor to Daedalus, aimed to redesign the interstellar fusion probe using updated physics and engineering knowledge. It broadened the fuel options, explored different fusion reaction types, and grappled with the deceleration problem, something Daedalus largely sidestepped by designing a flyby rather than an orbital mission. Slowing down at the destination requires roughly as much energy as speeding up, which means a full interstellar mission with orbital insertion needs about twice the propulsion capability of a one-way flyby. The Icarus team studied a concept called a magnetic sail for deceleration, a large loop of superconducting wire that generates a magnetic field, which then interacts with the interstellar medium and the charged particle environment of the destination star to create drag and slow the craft. It's the interstellar equivalent of a parachute, deployed not in air, but in the thin plasma that pervades the space between stars. What has changed since Daedalus that makes fusion more credible today is the progress in fusion research itself. In December 2022, the National Ignition Facility in California achieved fusion ignition for the first time in history, meaning the fusion reaction produced more energy than the laser energy delivered to the fuel target to start it. It was a milestone that had taken decades to reach. Commercial fusion power companies are now attracting serious investment and are pursuing reactor designs that could be operational within the 2030s or 2040s. Fusion still hasn't been achieved in a sustained, practical way, but the gap between where we are and a working fusion engine is shrinking in a way it wasn't in the 1970s. A working fusion reactor doesn't automatically give you a fusion rocket. The engineering of a fusion drive, where the reaction must not just sustain itself, but also be directed to produce thrust efficiently, is a separate and harder problem. But fusion ignition being achieved on Earth means the first domino has fallen. And that matters. One of the most ingenious propulsion ideas ever conceived, and one of the most troubling to examine closely, is the Bussard ramjet, proposed in 1960 by physicist Robert W. Bussard in a paper called Galactic Matter and Interstellar Flight. The concept starts with a basic observation. The space between stars is not truly empty. It contains thin clouds of hydrogen gas, averaging roughly 1 atom per cubic centimeter. It's an incredibly low density, far lower than the best vacuum achievable in any laboratory on Earth. But it's hydrogen, and hydrogen is fusion fuel. Bussard's idea was to collect that hydrogen on the fly as the spacecraft moved, feed it into a fusion reactor, and use the fusion products as exhaust. The ship would never run out of fuel because the fuel would be everywhere it traveled. The collection system would be an enormous electromagnetic funnel, a magnetic scoop potentially hundreds of kilometers or even thousands of kilometers in diameter, deployed ahead of the spacecraft. As the ship moved forward, it would sweep this funnel through space, gathering hydrogen atoms, funneling them into the fusion chamber, burning them, and accelerating. The faster it went, the more hydrogen it collected, and the more thrust it could produce. In theory, a ramjet could accelerate indefinitely, approaching the speed of light without any practical fuel limit. The Bussard ramjet captured imaginations immediately. It appeared in science fiction repeatedly, most notably in Paul Anderson's 1970 novel Tau Zero, where a runaway ramjet keeps accelerating until it's traveling at a significant fraction of the speed of light, and the crew experiences time dilation on a cosmic scale. The idea felt complete, even beautiful, a spacecraft that feeds on the very medium it travels through. The physics, unfortunately, is more complicated than the elegance suggests. The first serious problem is the density of interstellar hydrogen. Bussard's original calculations assumed a density that turned out to be too optimistic. The interstellar medium is patchier and sparser than early estimates suggested, and the average hydrogen density in many regions is too low to provide enough fuel for thrust. A 2025 analysis found that for a ramjet to function at all, the magnetic scoop would need to span something like 150 million kilometers, roughly the distance from the Earth to the Sun, just to collect enough hydrogen at realistic ISM densities to generate meaningful thrust. The second problem is drag. The same magnetic funnel that collects hydrogen also interacts with it before the hydrogen reaches the fusion chamber, and some of that interaction creates drag on the spacecraft. At certain speeds, the drag from collecting hydrogen could equal or exceed the thrust from burning it, creating a natural speed limit that makes the idea of indefinite acceleration impossible. The third problem is the fusion reaction itself. Bussard assumed proton-proton fusion, the same reaction that powers the Sun. But the proton-proton reaction is extraordinarily slow. The Sun only powers itself as well as it does because it has an incomprehensible mass of hydrogen maintained at incomprehensible temperatures and pressures for billions of years. A spacecraft engine has none of those advantages. The proton-proton reaction in an engine-sized device would produce negligible energy. Later variants of the ramjet concept proposed using catalysts or different reactions, or combining the collected hydrogen with onboard fuel rather than relying on it entirely. These modified designs are somewhat more plausible, but they lose the core appeal of the original idea: unlimited fuel. The honest conclusion from today's physics is that a pure Bussard ramjet faces obstacles that are probably fundamental rather than merely technical. The idea remains one of the most fascinating in the field, but as a practical interstellar vehicle, it likely doesn't work. Every propulsion method has involved extracting energy from matter through chemical reactions, fission, or fusion. But there's a category of reaction that dwarfs all of those: matter-antimatter annihilation. Antimatter is a real physical thing, not a science fiction invention. Every particle of ordinary matter has a corresponding antiparticle with the same mass but opposite properties. Opposite electric charge, opposite quantum numbers. The antiparticle of an electron is a positron. The antiparticle of a proton is an antiproton. When a particle and its antiparticle meet, they annihilate each other entirely, converting 100% of their combined mass directly into energy. No other reaction comes close to this efficiency. By comparison, chemical combustion converts roughly 1 part in a billion of fuel mass into energy. Nuclear fission converts about 0.1%. Fusion, around 0.3 to 0.7%. Antimatter annihilation, 100%. The energy density of antimatter propellant is roughly 10 billion times greater than chemical fuel, and about 1,000 times greater than fusion fuel. A spacecraft fueled by antimatter annihilating equal amounts of matter and antimatter in a controlled engine, could theoretically reach a significant fraction of the speed of light. A milligram of antimatter, less than a speck of dust, contains as much energy as 43 tons of chemical explosive. A few grams of antihydrogen could theoretically fuel an interstellar probe. So why isn't this the obvious answer to interstellar travel? Because making antimatter is extraordinarily difficult, extraordinarily expensive, and extraordinarily inefficient. Antimatter doesn't exist in nature in accessible quantities. The universe contains some, but almost entirely in environments we cannot reach or harvest. In cosmic ray interactions, in brief flashes near neutron stars, in the jets of active black holes. To make antimatter on demand requires particle accelerators. Protons are fired at high energy into a target, and the resulting particle shower contains a small fraction of antiprotons that can be captured and stored in magnetic traps. CERN in Geneva can produce about 10 nanograms of antiprotons per year. NASA's Marshall Space Flight Center has estimated that 1 gram of antimatter currently costs about $62.5 trillion to produce with current accelerator technology. Even with optimistic improvements, the production rate and cost are so far from what interstellar propulsion would require that there is currently no credible path to building an antimatter-fueled starship. A modified approach called antimatter catalyzed fusion offers a more near-term possibility. Instead of using antimatter as the primary fuel, a tiny amount, micrograms rather than grams, is used to trigger and ignite a fusion or fission reaction that provides the bulk of the energy. This dramatically reduces the antimatter requirement while still capturing much of the efficiency benefit. NASA analyses have suggested that antimatter catalyzed systems could be feasible with production improvements that are plausible within the coming decades, with per-mission antimatter costs potentially dropping to the tens of millions of dollars rather than trillions. The deeper issue with antimatter is storage. Antihydrogen must be contained in a magnetic trap, never touching the walls of its container, because contact with ordinary matter destroys both instantly in an annihilation flash. Holding antimatter stable for years or decades in a spacecraft that will experience vibrations, micrometeorite impacts, and radiation exposure is a solved problem in principle. CERN has trapped antihydrogen for significant periods, but keeping it stable at mission scale is another matter entirely. Any breach in containment is catastrophic. An antimatter engine aboard a spacecraft is, by design, carrying the most energetically dense fuel imaginable with zero tolerance for accidents. Most propulsion methods try to make the journey shorter, but there's a radically different philosophy that doesn't compete with speed at all. Instead of getting there faster, build a spacecraft that can sustain human life for as long as the journey takes, however long that turns out to be. A generation ship, sometimes called a world ship, is essentially a self-contained civilization in space. It travels at whatever speed current technology allows, which might mean the journey takes 500, 1,000, or even 10,000 years. The people who board the ship at departure know they will never arrive. Their children and grandchildren and great-grandchildren, born and raised aboard the vessel, will be the ones who eventually see the destination star grow in the viewports and make contact with whatever they find there. The idea isn't new. Science fiction writers proposed it in the early 20th century, and serious academic study has been underway for decades. What makes it genuinely interesting now is that the engineering challenges, while immense, are not physically impossible in the way that, say, warp drives currently are. A generation ship doesn't require physics we don't understand. It requires engineering we don't yet have, but in domains where progress is tangible, including life support, closed ecological systems, structural materials, and energy generation. In November 2024, the Initiative for Interstellar Studies launched a design competition called Project Hyperion, specifically for generation ship concepts. The competition attracted entries from architects, engineers, anthropologists, and urban planners worldwide. Winners were announced in July 2025, with entries judged on engineering rigor, social sustainability, and architectural integration. The winning designs treated the ship not just as a vehicle, but as a habitat, a place where communities form, cultures evolve, and generations live full lives rather than merely surviving in transit. That human dimension is the hardest problem of the generation ship. Engineering a closed-loop life support system is difficult but solvable. The ISS has operated one for decades on a small scale. Generating power from an onboard nuclear reactor over centuries is technically feasible. Providing enough food through hydroponics and controlled agriculture in a limited space is being actively studied for long-duration spaceflight. But maintaining social cohesion, psychological health, and purposeful governance across hundreds of generations in an isolated, enclosed environment is a problem that has no engineering solution. It's a problem of culture, psychology, and political philosophy. Population studies suggest that a generation ship would need at minimum several hundred people, and preferably several thousand, to maintain enough genetic diversity and social complexity to arrive at the destination as a functional civilization rather than a traumatized remnant. A ship housing thousands of people with agriculture, water recycling, social spaces, medical facilities, and redundant engineering systems across a journey of potentially hundreds of years would be an engineering feat of extraordinary scale. The mass would be in the millions of tons. The structural challenges alone, keeping such a vessel intact for centuries against micrometeorite erosion, radiation damage, and mechanical fatigue, would require materials and fabrication methods not yet available. One proposed version is the Ensman Starship, a concept from the 1960s that called for a vessel 600 meters long carrying an initial crew of 200, powered by deuterium fusion, and designed for the crew to expand the population during transit. Others have proposed using a hollowed-out asteroid as the hull, taking advantage of the natural radiation shielding of solid rock. The generation ship concept forces an uncomfortable question. Is it ethical to create humans, through reproduction during the voyage, who had no choice in the matter, destined to spend their entire lives in transit on a mission decided by their distant ancestors? This isn't hypothetical hand-wringing. It's a genuine philosophical question that any serious generation ship proposal must answer, and there's no consensus. Some argue that life lived meaningfully on a ship is no less valid than life lived on a planet. Others argue that consigning future generations to an existence they didn't choose is a form of harm. The debate is real and unresolved, A sleeper ship tries to solve the generation ship's social and ethical problems by simply putting the crew into a form of suspended animation for the duration of the journey. If you never experience the passage of time, a 1,000-year trip doesn't feel any different from a night's sleep. Suspended animation is not science fiction in the sense that it's biologically impossible. Nature does versions of it. Tardigrades, which are microscopic animals sometimes called water bears, can survive complete desiccation, vacuum, and radiation by entering a state of almost no metabolic activity for decades. Wood frogs in North America survive winter by allowing 65% of their body water to freeze solid. Their heart stopped, their breathing ceased, reviving completely when temperatures rise. Ground squirrels hibernate for months with metabolic rates reduced to a tiny fraction of their normal levels. For humans, the path to suspended animation is less clear. The most studied approach involves deep hypothermia, cooling the body to temperatures where metabolic processes slow dramatically. Some surgeons already use therapeutic hypothermia in cardiac surgery, temporarily cooling patients' bodies to buy time during complex procedures. But cooling a human body to the point of suspended animation and keeping them stable for years introduces catastrophic risks. Ice crystal formation in cells causes mechanical damage. Extended cessation of circulation affects the brain in ways that are not fully reversible. Complete suspension for more than a few hours, let alone years or centuries, is beyond current medical knowledge. The most plausible near-term approach isn't true suspended animation so much as deep torpor, reducing metabolic rates by 50 to 70% through a combination of cooling and metabolic suppression drugs, similar to natural hibernation in mammals. At that level of reduction, a person can be maintained for weeks or potentially months. SpaceWorks, an aerospace company, conducted a NASA-funded study on applying this kind of torpor to long-duration spaceflight, concluding it could dramatically reduce the life support requirement for a crew during transit. They weren't proposing centuries of sleep, just months, enough to make a trip to Mars more manageable. Scaling that to interstellar timescales would require advances in our understanding of cellular metabolism, organ preservation, and neural function that may or may not be achievable. Some researchers believe the problem is fundamentally solvable, that hibernation is a biological mode that could be induced in humans with the right pharmacological triggers, just as it's induced in other mammals. Others believe the human nervous system has characteristics that make genuine long-term suspended animation qualitatively impossible. A compromised design combines aspects of both approaches. A small rotating crew manages the ship, while the rest of the population travels in reduced metabolism torpor, rotating the sleeping and waking populations on cycles that keep no one awake for too long. This reduces the social complexity of a pure generation ship, while distributing the burden of consciousness across the voyage. There's also the possibility that medical advances over the coming centuries could solve the suspended animation problem in ways we can't currently predict. Nanotechnology that repairs cellular damage continuously, gene therapies that suppress aging, or entirely different preservation mechanisms not yet imagined might make a sleeper ship technically feasible long before a pure speed-based solution is available. There is a proposal that departs from anything that looks like conventional spaceflight and enters territory that is either genuinely revolutionary thinking or profound speculation, depending on who you ask. If the fundamental obstacle to human interstellar travel is the fragility and needs of biological bodies, their need for food, water, warmth, air, medical care, psychological stimulation, and their tendency to age and die, then one response is to stop sending biological bodies and start sending minds without bodies. The idea is this: if human consciousness can be fully described as information, the pattern of neural connections, the weights of synapses, the accumulated memories and personality that constitute a person, and if that information can be digitally encoded and transmitted or stored, then you could potentially upload a human mind to a computer, send that computer on an interstellar spacecraft, and reconstruct the person at the destination. At the destination, that mind could be run in a simulated environment during transit, run at any speed the hardware allows, which could mean experiencing years of subjective time during a trip that takes centuries in the outside world, or alternatively being kept dormant and instantiated only upon arrival. A crew of several hundred people could travel as a few terabytes of data on a spacecraft that masses kilograms rather than millions of tons. Upon arrival, they could be housed in robotic bodies, printed biological bodies grown from stored genetic material, or a virtual environment until physical infrastructure is established. There's a further extension of this concept that doesn't even require a spacecraft in the conventional sense. Radio waves also travel at the speed of light, and while that means they can't outrun light speed travel, they are far cheaper and easier to aim than a physical object. If a mind can be encoded as data, it could theoretically be transmitted as a radio or laser signal to a destination that already has the hardware to receive and run it. A kind of colonization by electromagnetic transmission rather than physical migration. The receiving station at the destination would need to have been established by prior physical mission, but once there, it could receive an unlimited number of minds from Earth without any additional spacecraft launches. The settlers travel at the speed of light. The implication is that if interstellar colonization ever becomes a serious project, the fastest and cheapest way to populate a newly reached star system might be to beam people there. Mind first, after the hardware is in place. This idea, called whole brain emulation or mind uploading, depends on a cascade of assumptions that are each individually uncertain and collectively unproven. The first is that consciousness is purely informational, that there's no irreducibly physical component to subjective experience that resists digital encoding. This is a contested philosophical question that neuroscience has not resolved. The second is that we can actually map a brain in sufficient detail to reproduce its function. The Human Connectome Project has spent years trying to map the wiring of even a small piece of a mouse brain, and the complexity is staggering. A complete human brain has roughly 86 billion neurons and perhaps 100 trillion synaptic connections. The third assumption is that a sufficiently accurate digital model of a brain would actually produce the subjective experience of the original person, and not merely a simulation that behaves identically without any inner life. None of these questions are settled, but none of them are ruled out by current physics either. They belong to a category of unknowns where the answer depends on future discoveries in neuroscience, philosophy of mind, and computing. If all three assumptions turn out to be correct, and some serious thinkers believe they will be, then mind uploading becomes the most practical interstellar travel method of all, by completely changing what we mean by a passenger. There's also a question of continuity. If you scan a brain, convert it to data, transmit it across 4 light years of space, and reconstruct it in a new substrate at the destination, is the being that wakes up at Alpha Centauri the same person who was scanned on Earth, or a copy? The original, if the scan was destructive, no longer exists. If it was non-destructive, there are now 2 versions of the same person, one at home, one 4 light years away. These aren't questions that physics can answer. They're questions about what personal identity means, whether it's tied to continuity of substrate or continuity of pattern. Different philosophical traditions give different answers. What's notable is that the question is no longer purely hypothetical. It's the question that would need to be answered before anyone could ethically proceed with such a mission. Whether that answer ever comes, and what it is, shapes whether this method ever moves from concept to practice. Beyond breakthrough starshot sail concept, there are other ways to use beamed energy from a stationary power source to drive an interstellar spacecraft. The common thread is separating the energy source from the spacecraft, keeping the heavy power-generating infrastructure at home, and beaming energy across space to a receiver on the spacecraft. One approach uses microwave beaming. A large array of microwave transmitters, assembled in space or on the moon, focuses microwave energy onto a receiver on the spacecraft. The receiver converts that energy into electricity, which powers an ion thruster or similar drive. The spacecraft itself carries almost no fuel, just the propellant for the thruster, which it gradually expels as the mission progresses. Because the energy source stays home, the spacecraft can be dramatically lighter than one carrying its own power plant. The limitation, again, is beam divergence. Beams spread out over distance. Laser beams spread less than microwave beams, which is why lasers are preferred for the starshot concept. But even laser beams eventually diverge enough that the energy reaching the spacecraft becomes insufficient. For a solar sail type mission, this doesn't matter. You're accelerating briefly and then coasting. But for a mission using continuous beamed power to run a thruster throughout the journey, the math becomes challenging once the spacecraft is more than a few light hours away. A more recent idea, proposed by Jeff Greason of the Tau Zero Foundation and detailed in a 2025 paper, uses relativistic electron beams instead of photons. Electrons accelerated to near the speed of light retain their coherence over long distances better than photons in some circumstances, and they carry their energy more efficiently. The concept is early in development, but it represents the kind of creative rethinking that the field regularly generates. Robert Forward, a physicist who spent much of his career on advanced propulsion concepts, proposed a variant of the laser sail architecture that addresses the deceleration problem for crewed missions. His design used a single enormous laser sail, then detached an inner portion of it as the spacecraft neared its destination. The detached ring section still illuminated by the original laser from home, reflected light forward onto the main sail to slow it down. It's a system of mirrors and timing that uses the same light beam to first accelerate and then decelerate the spacecraft without carrying any additional fuel. The engineering complexity is severe, but the physics works. One aspect of interstellar travel that sometimes gets lost in the engineering discussions is time dilation. The genuine slowing of time at speeds approaching light. It's not a trick or an approximation. It's a confirmed property of the universe, verified by experiments ranging from atomic clocks on aircraft to the precise calibration requirements of GPS satellites. At low speeds, the effect is negligible. At 10% of the speed of light, the time dilation factor is about 0.5%, barely noticeable over a journey. At 50%, time on the spacecraft runs about 87% as fast as time on Earth. At 90%, 44%. At 99%, roughly 14%. At 99.9%, about 4.5%. The closer to the speed of light, the more dramatic the compression. What this means in practice is that a spacecraft traveling at 99.9% of the speed of light would travel 4.24 light years to Proxima Centauri in about 4.24 years from Earth's perspective. But the crew aboard would experience only about 67 days. The universe has, from the crew's point of view, contracted in front of them. Space itself thins out in the direction of travel. At sufficiently high fractions of the speed of light, a human crew could theoretically cross the galaxy, which is around 100,000 light years, in a single human lifetime of about 70 years. From Earth's perspective, 100,000 years would pass. The crew would return to a world their species might not have survived. This makes extreme velocities both more and less appealing. The crew experiences a manageable trip, but they return to a future they can't reconnect with. Every friend, every family member, every institution they knew is gone. The civilization that sent them may not exist in any recognizable form. This isn't a physics problem, it's a deeply human one. More practically, time dilation becomes relevant to any interstellar proposal that aims at a significant fraction of the speed of light. At 20% of light speed, Breakthrough Starshot's target for the sail probes, the time dilation effect is small enough to be almost negligible. But for crewed missions targeting 50 or 80 or 90% of light speed, the asymmetry of experience time becomes one of the central facts of the mission that every other planning decision must account for. The closer any spacecraft gets to the speed of light, the more problems compound beyond just the energy requirements. The first is radiation. As the spacecraft moves faster, the photons of the cosmic microwave background radiation get blue shifted in the forward direction. At low speeds, this radiation is harmless microwave energy. But at 50% of light speed, those photons blue shift into infrared. At 90%, into visible light. At 99%, into ultraviolet and X-rays. At extreme fractions close to light speed, the forward-facing side of the spacecraft would be bathed in hard gamma radiation, intense enough to be instantly lethal to any unshielded crew. Interstellar medium particles compound the problem. The thin hydrogen gas between stars is harmless at low speeds, but at a significant fraction of the speed of light, Each hydrogen atom encountered carries relativistic kinetic energy from the spacecraft's perspective. At 99% of light speed, a single hydrogen atom hits with the energy of a cosmic ray particle. Encountering the average density of interstellar hydrogen at that speed would be like flying through a constant stream of radiation. Any material facing forward erodes rapidly. Proposed solutions include electromagnetic deflectors, using powerful magnetic fields to sweep charged particles out of the ship's path, and physical shields made of hydrogen or water ice, which could absorb particle impacts and be gradually replenished by scooping material from the interstellar medium. At very high speeds, even these solutions run into limits. The erosion rate of even the best shielding materials at relativistic speeds is a serious ongoing research problem. The practical implication is that there may be a sweet spot for interstellar travel speeds, fast enough to reach the destination in a meaningful time frame, but slow enough that radiation and erosion are manageable. Current estimates suggest that range might be somewhere between 10 and 30% of the speed of light, where the travel time to Proxima Centauri is between 14 and 42 years. Radiation environments are harsh but potentially manageable with shielding, and the energy requirements, while enormous, are not completely beyond the realm of future engineering. General relativity, Einstein's theory of gravity, published in 1915, is remarkably permissive about what kinds of structures space-time can theoretically contain. The equations allow for solutions in which space-time is curved so severely that two distant points become connected by a tunnel, a bridge through the geometry of the universe, rather than a path across its surface. These structures are called Einstein-Rosen bridges, or wormholes. The name comes from an analogy. Imagine a sheet of paper with 2 points, one at each end. The distance between them along the surface is large, but if you fold the paper so the 2 points touch, you can pass through a hole from one side to the other directly. A wormhole does the same thing with the fabric of space-time itself. In 1988, physicist Kip Thorne, who would later win the Nobel Prize for his work on gravitational waves, and his student Mike Morris published a paper in which they worked out the mathematics of a traversable wormhole in detail. Unlike the Einstein-Rosen bridge discovered in the 1930s, which collapses before anything can travel through it, a traversable wormhole could in principle remain stable and open long enough for a spacecraft to pass through. The problem is what it takes to keep such a wormhole open. The mathematics requires a form of matter with negative energy density, a material that would push space apart rather than pulling it together, the opposite of every known form of matter and energy. This exotic matter, as physicists call it, is not merely unavailable, it may not exist in the forms or quantities required. Quantum field theory does produce situations where negative energy densities can occur, such as the Casimir effect between closely spaced metal plates, but the amounts are fantastically small, and scaling them to the levels needed for a macroscopic traversable wormhole appears physically impossible with any known mechanism. Whether exotic matter in usable quantities exists somewhere in the universe, or could be manufactured by a sufficiently advanced technology, is unknown. Physicists don't have proof that it can't exist. They have a strong suspicion based on everything they know about how matter and energy behave, that it doesn't. That's a meaningful distinction. The door is not open, but it's also not locked with a certainty that physics can fully endorse. If traversable wormholes did exist and could be accessed, the implications for interstellar travel would be absolute. You don't travel across space. You step through a door and arrive. No fuel, no radiation, no decades of transit time. Every star in the galaxy becomes, in principle, as accessible as the next city. It's the most complete solution to interstellar travel that the equations of general relativity offer, and also the one most completely beyond any technology that can be currently imagined. In 1994, physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity that described a solution to Einstein's equations allowing faster-than-light travel, not by moving a spacecraft through space at superluminal speed, which special relativity prohibits, but by warping the space around the spacecraft itself. The mechanism works like this. Space-time is contracted in front of the spacecraft and expanded behind it. The spacecraft sits inside a flat, undistorted bubble of space. The bubble, together with everything inside it, moves through the universe. From the perspective of the passengers inside the bubble, they're not moving at all. Space is moving around them. Because the limit on the speed of matter applies to objects moving through space, not to space itself moving, the argument goes, the Alcubierre drive doesn't violate special relativity. The math is genuine, and the paper was published in a peer-reviewed journal and has been extensively analysed in the decades since. Inside the warp bubble, passengers experience no acceleration forces, no time dilation relative to Earth, no radiation from relativistic flight through interstellar matter. All of the problems that afflict high-speed conventional travel simply don't apply, because the spacecraft isn't actually moving relative to its local space. The physics inside the bubble is completely normal. The problem, as with traversable wormholes, is the exotic matter requirement. Generating and maintaining the space-time distortion of the Alcubierre bubble requires a distribution of negative energy density in the bubble wall. Alcubierre's original calculations implied a negative energy requirement equivalent to the mass energy of an object the size of Jupiter. Former NASA physicist Harold "Sonny" White later reformulated the geometry of the warp bubble and reduced the theoretical energy requirement dramatically to potentially just a few hundred kilograms of exotic matter. Though his calculations have been debated. In December 2025, White and colleagues published a new paper in Classical and Quantum Gravity introducing what they called an interior flat cylindrical nacelle warp bubble. This updated design distributes the required exotic energy into separate engine-like pods surrounding a flat, stable interior, rather than a single donut-shaped ring. It preserves the core Alcubierre properties, no tidal forces, no time dilation, and normal conditions inside, while potentially making the geometry more manageable from an engineering standpoint. The fundamental obstacle remains. No form of matter or energy known to physics produces negative energy density at macroscopic scales, and in the amounts required. Quantum effects can produce small regions of negative energy locally, but quantum inequalities, including mathematical constraints that arise from the same quantum field theory that allows a negative energy in the first place, appear to severely limit how long and how large such regions can be. Whether some future theory of physics transcends those limits is unknown. It's one of the questions where the honest answer is, we don't know enough yet to say whether this is permanently impossible or merely currently inaccessible, before getting to the question of what happens when a probe or crew arrives at another star. There's an intermediate idea worth examining that sits right at the boundary between telescope and mission. One that requires reaching a very specific location within our own solar system, and that could change what we know about nearby star systems long before any probe physically arrives. Einstein's general relativity predicts that massive objects bend light. The Sun, with its enormous mass, bends light from distant objects that pass close to its surface. This bending acts like a lens. If you could position a spacecraft directly on the opposite side of the Sun from a target star, at the focal point where the Sun's lensing effect concentrates the incoming light, that spacecraft would effectively sit at the focus of the largest telescope in the solar system. The Sun itself would be the optical element. The math shows that this focal point begins at roughly 550 astronomical units from the Sun, about 550 times the Earth-Sun distance, or approximately 51 billion miles. Past that distance, looking back toward the Sun with a modest-sized telescope, you can exploit the gravitational lensing effect. The amplification is extraordinary. Calculations show it could provide enough resolution to image the surface of an exoplanet orbiting Proxima Centauri in enough detail to see continent-scale features, and potentially vegetation or ocean patterns if they exist. This is not interstellar travel. The spacecraft would still be within our own solar system, just much further out than any mission has gone, but the information it could return would be transformative. Instead of sending a probe to Alpha Centauri on a 20-year journey and getting back a few hours of flyby data, a solar gravity lens mission could potentially spend years gathering high-resolution imagery of the target planetary system from this focal vantage point, returning data continuously. NASA has conducted serious feasibility studies on such a mission. The challenge is getting to 550 astronomical units in a reasonable time frame. Voyager 1, after more than 47 years of flight, has reached about 165 astronomical units. Getting to 550 astronomical units within 25 to 30 years would require a new propulsion approach, either a closed solar pass to slingshot a spacecraft outward at high speed, or a solar sail deployed near the Sun during a perihelion approach, or a nuclear thermal stage that dramatically increases departure velocity. None of these are beyond current technology at the required scale, which is why the concept has attracted serious study. A solar gravity lens telescope wouldn't replace a physical probe to another star, but it could tell us, before we go, whether there's something worth looking at more closely. It could be the scouting mission that precedes the true interstellar one. A way of answering some of the biggest questions about nearby worlds, from a position still within reach of current or near-term propulsion. Alongside the British Interplanetary Society's Daedalus study, the United States had its own serious technical investigation into interstellar missions. One conducted in the late 1980s under a joint study by the US Naval Academy and NASA, called Project Longshot. The target was Alpha Centauri, 4.37 light-years away. The proposed spacecraft would use a nuclear fission reactor for onboard power and a fusion pulse engine for propulsion, not the pure fusion drive of Daedalus, but a hybrid design that used fission to generate the electricity needed to initiate fusion micro-explosions, which in turn provided thrust. The mission was designed as a flyby, not an orbital insertion, still the more achievable version of the problem, since slowing down requires as much energy as speeding up. Longshot's projected cruise speed was about 4.5% of the speed of light. At that velocity, the journey to Alpha Centauri would take approximately 100 years. The spacecraft would weigh about 400 tons fully fueled, and the design called for launching it from Earth orbit using a large conventional rocket system to deploy the components, then assembling and fueling it in orbit before departure. One notable aspect of Longshot was the attention given to autonomy. A spacecraft 4 light-years away cannot be operated in real time from Earth. The signal delay alone is over 4 years each way, meaning any instruction sent from Earth would take 4 years to arrive, and any response would take another 4 years to return. For a flyby mission, there's no time to send instructions and wait for responses anyway. The spacecraft would need to conduct its science mission entirely on its own, based on programming installed before departure and its own onboard intelligence. The Longshot study was candid about what its 1980s-era technology could and couldn't achieve. The fusion ignition challenge was acknowledged but treated as a future problem to solve. The study was oriented toward laying out the mission architecture on the assumption that fusion ignition would eventually be cracked. 30 years later, that assumption has been validated by the National Ignition Facility, though fusion propulsion still requires considerable additional development beyond ignition in a lab. What makes Longshot historically interesting is less the specific design, which has since been superseded by more detailed analyses, and more what it represents. A straightforward, non-ideological engineering document produced by serious professionals who concluded that interstellar travel was not just science fiction, but an engineering problem that could be approached methodically. The conclusion wasn't someday maybe, it was, here is a design, here are the numbers, here are the open technical problems. That shift in tone, from wishful thinking to engineering analysis, represents the maturation of interstellar mission planning as a genuine field. One of the most persistently underestimated challenges in interstellar mission planning is that arriving at a destination star isn't the same as orbiting it, studying it, or landing on anything nearby. If a spacecraft arrives at Proxima Centauri traveling at 20% of the speed of light with no means of slowing down, it flies through the system in a matter of hours and continues into deep space beyond. All the data it collects comes from that brief window of proximity. That's valuable, but it's limited. Every propulsion system that can accelerate a spacecraft to interstellar speeds faces the mirror problem on the other end. How do you slow down? For unmanned probe missions, you can potentially tolerate a flyby. Breakthrough Starshot is explicitly designed this way. But for any mission that involves taking up orbit, deploying landers, or keeping a crew in a stable position long enough to do sustained science, deceleration is not optional. The energy required to decelerate from 20% of light speed to orbital velocity is the same as the energy required to accelerate to 20% of light speed in the first place. For a beam sail craft, the energy came from an Earth-based laser. There's no laser array at the other end. For a fusion rocket, the fuel for deceleration must be carried along from the start, which roughly doubles the propellant requirements and dramatically increases launch mass. Robert Forward's reflected laser architecture, mentioned earlier, was one creative solution. Another approach involves what's called a magsail or magnetic sail, a loop of superconducting wire deployed from the spacecraft that generates a large magnetic field. This field interacts with the stellar wind of the destination star and the charged particle component of the interstellar medium, creating drag that gradually slows the craft. Physicist Robert Zubrin, who has proposed many interstellar mission concepts over the years, calculated that a sufficiently large magnetic sail could decelerate a fusion-powered probe from a significant fraction of the speed of light over a period of years or decades, without consuming any additional propellant. The numbers for magsail deceleration are sensitive to the conditions in the destination system, the strength and density of the stellar wind, the local interstellar medium density, and to the size of the sail, which can theoretically be enormous since it's a magnetic field rather than physical material. The concept doesn't require new physics, only superconducting wire technology that is already advancing, and the ability to deploy a very large coil in space. A completely different approach to the deceleration problem doesn't involve the spacecraft at all. Instead, a second beam array, built and deployed in the destination system, potentially by robotic precursor probes sent ahead decades earlier, meets the arriving craft and decelerates it using the same directed energy principle that accelerated it. This requires sending the precursor missions first, waiting decades for them to arrive, for them to construct the deceleration infrastructure autonomously, and only then sending the primary mission knowing that a landing pad will be waiting. The coordination across decades of flight time is an enormous operational challenge, but the physics is clean. The deceleration problem is also why speed limits matter. The faster a spacecraft travels, the harder it is to stop. At 1% of the speed of light, a magnetic sail or a reasonable onboard propulsion reserve can handle deceleration. At 20%, the engineering becomes very difficult. At 50%, it becomes a dominating mission constraint. The ideal interstellar mission speed isn't necessarily the fastest achievable. It's the fastest that allows the mission to actually accomplish something meaningful at the destination rather than passing through it like a bullet through a fog. No discussion of interstellar travel methods is complete without asking where they would actually take us, and why those destinations matter enough to justify the effort. The obvious first target is the Alpha Centauri system, because it is simply the closest. The triple star system, consisting of Alpha Centauri A, Alpha Centauri B, and the more distant red dwarf Proxima Centauri, sits about 4.24 to 4.37 light-years away. Proxima Centauri hosts at least 2 confirmed planets. Proxima b, discovered in 2016, orbiting in the habitable zone, and Proxima d, a smaller world closer in, confirmed in 2022. There may be more. Whether Proxima b is actually habitable is deeply uncertain. Proxima Centauri is a red dwarf, smaller, cooler, and much less luminous than the Sun. For a planet to have liquid water, it must orbit much closer to such a star, which means it's close enough to be tidally locked. One side permanently facing the star, one side permanently in darkness. Whether that creates a viable environment for life, possibly a belt of temperate conditions at the terminator between the two sides, or a frozen, airless rock is unknown. The star is also highly active, erupting in powerful flares that could strip away a planet's atmosphere over geological timescales, unless the planet has a strong magnetic field. Alpha Centauri A and B are more Sun-like, making any planets they might host potentially more Earth-like in their environments. But confirmed planet detections around these two stars have been elusive. Proposed candidates haven't held up to scrutiny, and the two stars orbit each other closely enough to make stable, long-period orbits around either one of them complex to analyze. The next tier of interesting targets includes Tau Ceti, about 11.9 light-years away, a single G-type star similar to the Sun that has multiple planet candidates, including possibly 2 in the habitable zone. Epsilon Eridani, about 10.5 light-years away, is a younger star that was for many years considered one of the most promising candidates for hosting a planetary system. And it has a confirmed debris disk, and likely at least one planet. TRAPPIST 1. A red dwarf 40 light-years away, has 7 known Earth-sized planets, 3 of which are in the habitable zone, the most potentially habitable planetary system yet identified beyond our own. What this landscape of targets reveals is that the question of interstellar travel isn't about one destination. It's about a survey, a sustained exploration of dozens of nearby star systems over centuries and millennia. Each system provides a data point in the larger question. How common is life in the universe? What conditions produce it? And are any of those worlds suitable for human presence? The answer to that question shapes everything about what kind of interstellar mission makes sense. If a world is already inhabited by complex life, the ethical implications of visiting it are profound and not straightforward. If a world is habitable but lifeless, it becomes a candidate for eventual colonization. If a world is geologically active, has water, but shows no biology, it tells us something important about the pathway from chemistry to life. Each category of discovery justifies a different kind of follow-up, and therefore different mission architectures. Breakthrough star shots flyby probes are appropriate for the first reconnaissance. Fusion-powered orbital missions are appropriate for the second phase, once we know what's there and want to look more carefully. Generation ships or large crewed missions represent the third phase, humanity physically extending itself to another star, and they become appropriate only when we know that the destination is worth the extraordinary cost and effort of sending people. Between the stars, space is not empty. It's thin, far thinner than any vacuum achievable in a lab on Earth. But it contains gas, dust, magnetic fields, and cosmic rays, and any spacecraft attempting to cross interstellar space will encounter all of them continuously for decades or centuries. The interstellar medium, or ISM, is composed primarily of hydrogen and helium in various states. In dense molecular clouds, the hydrogen is in molecular form. In more diffuse regions, it's atomic. In hot, ionized regions near active stars, it's plasma. The space between stars in our local neighborhood, the region through which any Alpha Centauri mission would travel, is part of what astronomers call the local bubble, a region of particularly low density ISM that our solar system sits within. This is actually favorable for travel. The ISM here is thinner than average, which reduces both the drag and radiation exposure for a fast-moving spacecraft. Even in the local bubble, a spacecraft moving at 20% of the speed of light encounters roughly 0.02 hydrogen atoms per cubic centimeter. That sounds negligible, but at 20% of light speed, each hydrogen atom the spacecraft hits carries considerable kinetic energy from the craft's perspective. The rate of collisions with atoms adds up, and at higher speeds, the effect becomes increasingly severe. Studies of the interaction between relativistic spacecraft and the interstellar medium, including a detailed analysis by researchers studying the breakthrough starshot concept, found that at 20% of light speed, erosion of the leading edge of a sail or spacecraft from atomic collisions is a significant engineering concern. Proposed solutions include shaping the spacecraft so that it presents the smallest possible cross-section in the direction of travel, coating the leading edges with erosion-resistant materials, using an electromagnetic deflector to ionize and redirect charged particles before they impact the spacecraft structure, or placing a thin sacrificial shield of material ahead of the spacecraft that absorbs most of the impacts and can be slowly consumed over the mission. Cosmic rays are a separate problem. These are high-energy particles, mostly protons, that travel through the galaxy at near-light speeds, produced by supernovae and other violent astrophysical events. The interstellar space between stars has a flux of cosmic rays higher than the radiation environment within our solar system, which is partially shielded by the heliosphere. A spacecraft in interstellar space for decades will experience elevated cosmic ray exposure, which damages electronics over time through cumulative ionization effects. Radiation-hardened electronics, redundant systems, and error-correcting memory architectures can mitigate this, but they add mass and complexity. Interstellar dust grains, tiny solid particles of silicate or carbonaceous material ranging from nanometers to micrometers in size, pose a different threat. At low speeds, a dust grain hitting a spacecraft is harmless. At high fractions of the speed of light, a single micrometer-sized dust grain carries kinetic energy comparable to a small explosive. The density of dust grains in the ISM is low enough that the probability of hitting a large one on any given day is small, but over a 20-year crossing, the accumulated exposure means statistically the spacecraft will almost certainly encounter dust events. Whether those events are survivable depends on the spacecraft design and the size distribution of dust in the specific region being traversed, something that varies across the ISM and is not uniformly mapped. These aren't fatal objections to interstellar travel. They are engineering requirements. Every spacecraft ever built has had to deal with its operating environment, and the engineering solutions have been found each time. Interstellar conditions are more extreme, and the solutions are harder, but the problem class is the same. Understanding the ISM in detail, its density, composition, dust distribution, and magnetic structure along any given route is itself a scientific mission that needs to precede or accompany any interstellar crossing. There's a category of interstellar mission proposal that doesn't try to send humans or even a fixed robotic probe across the void. Instead, it proposes sending a seed. A von Neumann probe, named for mathematician John von Neumann, who in the 1940s formalized the concept of self-replicating machines, would be a spacecraft capable of arriving at a distant star system, mining raw materials from asteroids or planets in that system, using those materials to build copies of itself, and sending those copies onward to other star systems. Each copy does the same at its destination. The fleet grows exponentially without requiring anything more from the civilization that launched the first probe. The energy and resources come from the universe itself, harvested along the way. The first probe could be sent at whatever speed current technology allows. Even at 1% of the speed of light, the replication and propagation timescale means that a civilization deploying von Neumann probes could survey the entire galaxy within a few million years. A blink in cosmic time. Add scientific instrumentation to each probe, and it becomes not just a relay network, but a galaxy-scale exploration system, reporting back continuously from thousands of star systems simultaneously. The challenges are primarily computational and engineering. Each probe must be capable of autonomous operation for centuries, of identifying and extracting useful materials from whatever it finds at its destination, of manufacturing complex electronics and mechanical systems from raw materials without any human assistance, and of building copies of itself with sufficient fidelity that the copies can do the same. None of these capabilities exist today, but each one is a direction in which technology is already moving. Robotic manufacturing is advancing rapidly. Autonomous decision-making by machines is advancing rapidly. The concept of in-space resource utilization for mining asteroids and processing their materials in space is moving from theory to early demonstration. Whether all of these capabilities can be combined into a self-replicating probe of any reasonable size is genuinely unknown, but the underlying technologies are not physically prevented from existing. The philosophical dimension of von Neumann probes is worth noting. If they work, a civilization doesn't need to travel to the stars itself. It populates the galaxy with its technology, which may eventually be more capable of understanding those environments than biological travelers ever could be. Whether that counts as exploration in any meaningful sense, or whether it's a kind of cosmic colonialism by machine, is a question without an obvious answer. But as a solution to the interstellar travel problem, it's the one that requires the least heroic physics. Just advanced engineering pushed far beyond where it is today. Some proposals for interstellar travel are really proposals about the scale of civilization required before interstellar travel becomes practical at all. A Dyson sphere, proposed by Freeman Dyson in 1960, is a megastructure, either a solid shell or a swarm of orbiting platforms, built around a star to capture all of its energy output. Our sun radiates about 3.8 times 10 to the 26th power watts of energy. Earth intercepts a tiny fraction of that. A Dyson sphere captures all of it. With that kind of energy at your disposal, powering the laser array required for breakthrough starshot at 1,000,000 times its planned scale becomes trivial. Fueling an antimatter production facility large enough to produce kilograms of antiprotons per year becomes feasible. Building a fleet of generation ships carrying millions of people becomes an affordable project rather than a civilization-defining effort. A stellar engine, sometimes called a Shkadov thruster, takes the Dyson sphere concept in a different direction. Instead of capturing stellar energy for use, it uses the radiation pressure of the star itself to slowly move the star through space. A large reflective structure on one side of the star reflects radiation back, creating a slight imbalance in the radiation pressure that acts on the star. Over millions of years, the star and its entire accompanying solar system drifts through the galaxy. Why would you want to move a star? If a dangerous object, such as a nearby supernova, an approaching rogue star, or a gamma ray burst in the galactic neighborhood, threatens your home system, a stellar engine gives you the ability to steer away from it on geological timescales. It also means you can, very slowly, navigate toward other star systems, closing the interstellar gap over millions of years through the movement of your home star rather than the launching of a spacecraft. These are not technologies for any civilization recognizable as human. They're proposals for what civilizations become over millions of years of development, what physicist Freeman Dyson called a Type 2 civilization on the Kardashev scale, one that commands the full energy output of its star rather than burning fossil fuels scraped from the surface of a single planet. Whether humanity ever gets there, and whether any civilization in the galaxy already has, is unknown. But they define the outer edge of what's physically imaginable, and they provide a kind of destination for a very long arc of technological history. One dimension of interstellar travel that receives less attention than propulsion, but is equally fundamental, is communication. A spacecraft crossing interstellar space doesn't just need to get there, it needs to send back what it finds. And a crewed ship doesn't just need to carry people, it needs to stay in contact with the civilization that launched it. The limitation is the speed of light. Radio waves, like all electromagnetic radiation, travel at 186,000 miles per second. That's extraordinarily fast by everyday standards. But at interstellar distances, it introduces delays that change the entire character of the relationship between a spacecraft and its home. A signal from a spacecraft at Proxima Centauri takes 4.24 years to reach Earth. A response takes another 4.24 years to return. Asking a question and getting an answer takes over 8 years. For a robotic probe on a pre-programmed flyby, this is inconvenient but workable. The mission completes on its own, and the data arrives years later. For a crewed mission of any duration, it means effectively total operational independence. The crew makes every decision on its own. Earth cannot manage the mission in any real-time sense. Mission control becomes a historical institution rather than an active partner. This has profound implications for mission design and crewed ship governance. A crew that is fully autonomous from Earth for years or decades isn't just a technical fact, it's a political one. Who do they answer to? What legal framework applies? What happens if the crew's interests and Earth's interests diverge? What if the crew decides upon arrival that they will not return? These are questions for which no current institution has answers, because no mission has yet operated under these conditions at this scale. For Signal itself, the engineering challenge is sending data across 4+ light years with enough power to be detectable. The deep space network's antennas can barely maintain communication with Voyager 1 at 165 astronomical units, using its 23-watt transmitter, a signal so faint that it requires the largest radio dishes on Earth operating in perfect conditions to detect. At 10,000 times that distance, the signal would be 100 million times weaker by the inverse square law. Maintaining any useful data rate over interstellar distances requires either a much more powerful transmitter, a much larger receiving array on Earth, or a laser-based communication system that concentrates energy in a tighter beam than radio. Laser communication, using focused laser beams rather than radio waves to carry data, is already being demonstrated for deep space missions. NASA's LLCD and LCRD experiments have shown laser communication dramatically outperforming radio for data rate. An interstellar probe using a highly focused laser transmitter could potentially maintain a usable data link back to Earth, though achieving the pointing accuracy required, keeping a laser aimed at a target the size of Earth from 4 light-years away, while moving at a significant fraction of the speed of light, is a formidable engineering challenge. There's a philosophical dimension to the communication problem that surfaces most acutely for crewed missions. Human beings are social creatures who define themselves partly through their relationships with others. A crew of people cut off from all contact with the rest of humanity, or maintaining contact only through messages exchanged years apart, is experiencing something genuinely novel in the human condition. The psychological literature on isolation is extensive, drawn from polar expeditions, submarine deployments, and space station missions, but nothing approaches the scale of interstellar isolation. The nearest analog might be the psychological experience of emigrants from pre-communication eras, who boarded ships knowing they might never receive news from home again. But even they arrived somewhere within months, among other people. An interstellar crew is isolated not just from home, but from all of humanity for their entire voyage. Designing the communication architecture for an interstellar mission isn't just about antennas and bandwidth. It's about what information the crew needs, what information Earth needs, and how the relationship between a ship and its originating civilization is maintained across the kind of distance where the light carrying news from one takes years to reach the other. There's something worth saying about why all of this effort, all of these decades of calculation and theorizing and studying propulsion systems for journeys that no one alive today will take, actually matters. The nearest known exoplanet to Earth, Proxima Centauri b, orbits within the habitable zone of its star. Whether it has liquid water, whether it has an atmosphere, whether it has anything that we would recognize as life, we don't know. Ground-based telescopes and even space telescopes cannot resolve a planetary surface at those distances. The difference between a barren rock and a world teeming with organisms is invisible from here, at 4.24 light-years. The only way to know, truly know, is to go. And if life exists there, the implications are total. It would be the end of the question of whether we are alone. Every religion, every philosophy, every political framework that has been built partly on the assumption of human uniqueness would face a new reality. The discovery of a second living world in the universe would be the most significant event in human intellectual history. Everything we thought we understood about our place in the cosmos would need to be reconsidered from the foundation up Not because the discovery would necessarily overturn any specific scientific theory, but because it would change the emotional and philosophical context in which all of those theories exist. We would know from that moment forward that life is not an accident that happened once in one corner of one galaxy. It would mean life is something the universe produces, given the right conditions, the way water flows downhill or hydrogen fuses under sufficient pressure. If life doesn't exist at Proxima Centauri b, if the planet is tidally locked, and its atmosphere has been stripped by the star's flares, and it's a frozen, airless rock, that finding also matters. It tells us something about how the habitability of red dwarf planets works, which constrains our estimates for how common habitable worlds are in the galaxy. Most stars in the galaxy are red dwarfs. If their planets are systematically uninhabitable for reasons we can confirm close up at Proxima, the odds of life being widespread narrow considerably. That narrows them is not the same as ruling them out. There are still hundreds of billions of other stars, but it changes the math. The next nearest candidates are tens of light years away, and beyond them, hundreds, and beyond them, thousands. The galaxy is full of stars, and their planets are common. We know this now from the data gathered by the Kepler and TESS space telescopes. Most stars have planets. A substantial fraction of those planets sit in orbits where liquid water could exist. The question isn't whether there are other worlds out there that could support life. There certainly are. The question is, what is on them? That question has an answer. It's written somewhere in the chemistry and biology of planets we haven't visited yet. Reaching it requires solving the engineering problem that humanity has been quietly working on for 60 years, and that this accounting of methods has tried to fully lay out. How do you cross 25 trillion miles to the nearest star? The honest conclusion is that there is no single method that does it all. Not yet. Breakthrough Starshot could send a probe within a generation, a tiny thing, a chip with a sail, screaming through Alpha Centauri's neighborhood and sending back a few hours of measurements. Fusion propulsion, decades further out if it develops on schedule, could eventually push larger probes at higher speeds with more capable instruments. Antimatter, if the production problem is cracked, could power missions that rival anything in science fiction while remaining within the laws of physics. Generation ships, slow but certain, could carry human civilization to a second home across centuries of voyage. A solar gravity lens telescope could tell us what we're going to find before anyone arrives. Von Neumann probes could map the entire galaxy across millennia without requiring any single heroic launch. And somewhere at the frontier of what our mathematics permits, the possibility of bending space itself has not been ruled out. No single generation will solve this problem, but no generation is being asked to. Each era adds a chapter, a new material that absorbs laser light a little better, a fusion confinement design that holds plasma a little longer, a computer small enough to navigate an interstellar crossing on the power of a small battery, a medical breakthrough that makes suspended animation more than a dream. Each chapter brings the next generation of researchers closer to the one that will actually make the crossing happen. The stars have been visible from Earth for as long as eyes have existed to look up at them. For almost all of that time, they were simply lights in the sky, named and mythologized, and navigated by, but fundamentally unreachable, as removed from human experience as the afterlife or the deep past. Now, for the first time in the history of life on Earth, a species is sitting down with equations and lasers and superconducting wire and calculating exactly how to get there. Not dreaming about it. Calculating. That's not nothing. That's the beginning of something that once started tends not to stop. If any of this leaves you wanting to go deeper on the physics, the engineering, the timelines, the worlds that might be waiting, subscribing keeps this kind of exploration coming. Every video is built to take the most important questions in space science and give them the time they deserve. Hit the button and don't miss what's next.